Okay, so it's time to start. The second speaker today is Professor Hiroki Matsui, and the title is Spectra of Derived Categories of Neutrino Schemes. So please start.
Thank you for the introduction. First of all, I would like to thank the organizers for giving me such a chance to talk in this seminar. Today, I will talk about the spectra of derived categories of Noetherian schemes. So in this talk, we define a topological space for a given triangulated category, and we apply it to the derived categories of Noetherian schemes. Okay, in this talk, always X denotes a Noetherian scheme, and we consider the derived category of perfect complexes on X, and we call this the perfect derived category. The motivation of this talk is the following problem. Recover some information about a scheme X from this triangulated category. This is the motivation of this talk. And it is known that we cannot reconstruct the scheme X from the triangulated category structure of the perfect derived category. Indeed, it is shown by Mukai that on an abelian variety X, there exists equivalence of triangulated categories between the perfect derived category of X and the perfect derived category of the dual of X. So there exists varieties X and X hat, which is not isomorphic, but their derived categories are equivalent. So we cannot reconstruct the scheme X from the triangulated category dpfx. On the other hand, Balmer proves that we can reconstruct the scheme X from dpfx using its tensor triangulated category structure. If we use the additional information about tensor product, we can reconstruct the scheme X from this category. And this is a consequence of Balmer's tensor triangular geometry. Okay. Now, let us briefly introduce Balmer's tensor triangular geometry. Let T tensor 1 be a tensor triangulated category. This means tensor for any object M and N, we have the tensor product, which is functorial and compatible with triangulated category structures. In this talk, we mainly consider this tensor triangulated category, the perfect derived category, and the derived tensor product, and the structure C. This triple defines a tensor triangulated category, and we always consider this category. The Balmer's tensor triangulated geometry studies a tensor triangulated category T by the corresponding topological space, spec tensor T, which is the set of prime-sig ideals of T together with some topology. And we call this topological space the tensor triangular spectrum, or we call this TT spectrum for short. Here, a proper subcategory P of T is called a prime-sig ideal if it satisfies the following three conditions. First condition means P is a sig subcategory. Namely, P is closed under K-tin direct summons 6 and mapping cones. And second condition means that P is ideal. For an object P of, for an object M of P and object N of T, their tensor product belongs to P. And the third condition means P is a prime ideal. If the tensor product of M and N belongs to P, then M over N belongs to P. As you can see, these last two conditions is an analog of ideal and prime ideal of commutative rings. This is a definition of prime-sig ideal, and the TT spectrum is a set of prime-sig ideal of T. And tensor triangle categories naturally appear in many areas of mathematics, such as commutative algebra, algebraic geometry, stable homotopy theory, and operator theory, and so on. So Balmer's tensor triangle geometry is studied in such areas of mathematics. The following theorem is the fundamental result in tensor triangular geometry. This result is due to Balmer. The first result is there exists an order preserving isomorphism between the set of radical sig ideals of T and the set of Thomason subsets of the TT spectrum. Here, the notion of radical sig ideals are defined similarly to radical ideals of commutative rings. And Thomason subset is almost the same as specialization closed subset of the TT spectrum. Indeed, if the topological space is Noetherian, Thomason subsets and specialization closed subsets are the same. Here, the left-hand side contains information of tensor triangle category structure of T, and right-hand side contains information of topological space of this topological space. So this theorem connects the tensor triangle category structure and the topological structure. And the second statement says that the TT spectrum is uniquely determined by this property. Namely, if a topological space X gives such a bijection, then this topological space X is homeomorphic to the TT spectrum. In this sense, the TT spectrum is uniquely determined by this property. For our perfect derived category, Thomason proves that there exists an order preserving isomorphism between the set of radical sig ideals of dpfx and the set of specialization closed subset of X. And the correspondence is given in this way. For a subset, for a radical sig ideal X, we have a specialization closed subset. We have this specialization closed subset. This is a union of support of object of X. Since this is a union of closed subset, this is a specialization closed subset. So this topological space X gives such a bijection, order preserving bijection. So by using the the second theorem, Balmer proved that the following result. For a Noetherian scheme X, there exists a homeomorphism between X and the TT spectrum, where the point X maps to these prime-seq ideas. S of X is a subcategory consisting of object F, whose stalk at X is isomorphic to 0. The point X corresponds to this prime-seq ideal. Actually, Balmer, now we only consider topological structure of TT spectrum, but Balmer also introduced a C-hop links on the TT spectrum. And he proved that this homeomorphism is actually an isomorphism of schemes. Therefore, this theorem gives a reconstruction of X from the tensor triangulated category structure of the perfect derived category, because the right-hand side is defined by using the tensor triangulated category structure. So X is reconstructed from this tensor triangulated category. So using additional structure, we can reconstruct the scheme X from the perfectly derived category. However, at least for me, tensor structures are too strong. For example, there are important triangulated categories without natural tensor structures. For example, the bounded derived category of coherent fields on X is a triangulated category, and this triangulated category do not have natural tensor structure. And also, the singularity category, which is a quotient of the bounded derived category by the perfect derived category, this category is also do not have a natural tensor structure. So to study these triangulated categories, we cannot use tensor triangular geometry. Also, the derived equivalences between two varieties appears as Fourier-Mukai partner in algebraic geometry. But such category equivalence do not preserve tensor structure in general. So to study such a Fourier-Mukai partner, we cannot use tensor triangular geometry. From this motivation, the aim of this talk is to define a tensor-free analog of prime-seq ideas, which we call prime-seq subcategories, and also define a topological space for a triangulated category without using tensor structures. And also, we apply this construction to the perfect derived category of X. This is aim of this talk. So before introducing prime-seq subcategories, let me give one observation. Let T be a tensor triangulated category with Noetherian TT spectrum. For example, the perfect derived category satisfies this condition. This is a tensor triangulated category and whose TT spectrum is Noetherian because it is isomorphic, it is homeomorphic to X. For such a tensor triangulated category T, we have the following proposition. Let P be a radical seq idea of T. Then P is a prime-seq ideal if and only if there exists a unique radical sick ideal I, which is properly containing P, such that there exists no radical sick ideal J between P and I. This condition is a little complicated, but the important point is prime sick ideals of T is determined by using order structure on the set of radical sick ideals. Because this condition only uses the inclusion relation between radical sick ideals. So prime sick ideals are determined by the order structure. And our strategy is to define prime sick subcategory is to replace radical sick ideals with sick subcategories. And there exists extra bits. We replace these radical ideals with sick subcategories. Okay, now let me give a definition of prime sick subcategories. Let T be a triangulated category. In this talk, we always consider this triangulated category. Let P be a sick subcategory. Then we say that P is a prime sick subcategory if there exists a unique sick subcategory X properly containing P, such that there exists no sick subcategories Y between P and X. Please compare this definition with the previous proposition. We replace these radical sick ideals with sick subcategory. Then we obtain the notion of prime sick subcategory. And denote by spec triangle T to be the set of prime sick subcategories of T. And we also define the topology on this set, whose closed subsets are of this form for some family of object E. G of E is defined in this way. This is a set of prime sick subcategories, which is not intersect with E. The intersection of E and P is empty. And then this defines a topology on this set. And we call this topological space the triangular spectrum of T. Yeah, this is a definition of topological space spec tensor T, spec triangle T. And actually, the definition of topology is similar to that of the TT spectrum. Indeed, for the definition of the topology on the TT spectrum, we use prime sick subcategories instead of prime sick ideals. So just replacing prime sick ideals with prime sick subcategories, we obtain the topology on the triangular spectrum. Let me give some remark about this topological space. We will see later that for a sick ideal P of the perfect derived category, P is prime sick ideal if and only if P is a prime-6 subcategory. So if we're restricting 6 ideals, prime-6 ideals and prime-6 subcategories are the same concept. And the triangle spectra satisfies similar properties to TT spectra. Indeed, in the introduction, I have introduced this theorem by Balmer, and the similar result holds for the triangular spectrum. So indeed, therefore, we can consider the prime-6 subcategories are tensor-free analog or tensor-free extension of prime-6 ideals. This is the definition of prime-6 subcategories. So the definition is a little complicated, and so it is difficult to understand what is a 6 subcategory, what is a prime-6 subcategory. So let me give one typical example of prime-6 subcategories. Let R be a commutative Noetherian ring. Then for any prime ideal of R, we consider this subcategory, S of P. This is subcategory of the perfect derived category of X consisting of object M, whose localization at P is isomorphic to 0. Then this subcategory is a prime-6 subcategory of the perfect derived category. Indeed, we can prove this statement as follows. By the result of Hopkins and Niemann, there exists an order-preserving isomorphism between the set of 6 subcategories and the set of 6 subcategories of the perfect derived categories of R and the set of specialization closed subsets. Yeah, actually, this isomorphism is a special case of the result of Thomason, this result. The fine case of result is given by Hopkins and Niemann. And the correspondence is given by taking support. By this isomorphism, S of P belongs to the left-hand side, which corresponds to a specialization closed subset W0, which is a set of prime ideal Q such that P is not contained in the closure of Q. S of P corresponds to W0 by this isomorphism. Then we consider this specialization closed subset. Then the inverse image of this specialization closed subset is a 6 subcategory, and this is a unique 6 subcategory satisfying this condition. There exist no 6 subcategories between S of P and this 6 subcategory. Indeed, using this order-preserving isomorphism, we can translate these properties to the language of specialization closed subset. And we can easily check that there exists no specialization closed subset between W0 and this specialization closed subset. So SOP satisfies this six subcategory satisfies this condition. And this condition means that SOP is a prime six subcategory by definition. This is a proof of this example. Okay, this is a definition of prime six subcategories and examples. Now, we concentrated on the perfect derived category and their perfect derived category and its prime six subcategories. So we consider a Noetherian scheme X. By Balmer's result, the TT spectrum, recall that by Balmer's result, the TT spectrum is homeomorphic to X. And the correspondence is given in this way. A point X corresponds to S of X. Therefore, every prime-sig ideal of the perfect derived category is of this form. S of X is this prime-sig subcategory, a prime-sig ideal. So it is natural to ask, for a point X, is S of X a prime-sig subcategory? This is a quite natural question, because this is a prime-sig ideal. So it is natural to ask whether this is a prime-sig subcategory or not. And the main theorem of this talk is the answer to this question. This is the main theorem. Let X be a Noetherian scheme. Then the first statement is the following. S of X is a prime-sig subcategory of the perfect derived category. This is the prime-sig subcategory. Balmer's result shows that S of X is a prime-sig ideal, but the main theorem says that this is also a prime-sig subcategory for any point X. So since S of X is a prime-sig ideal, the first statement says that prime-sig ideals implies prime-sig subcategory for the perfect derived category. The second statement is the converse. Let P be a sig ideal of the perfect derived category. If P is a prime-sig subcategory, then P is a prime-sig ideal. So the first statement says that prime-sig ideals are prime-sig subcategories, and the second statement says that prime-sig ideal, which is also a prime-sig subcategories, are prime-sig ideals. So if we consider sig ideals, then the converse implication holds true. In particular, P is equal to S of X for some point X, because P is a prime-sig ideal. So this is the main theorem of this talk. In this today, we always consider the perfect derived category, but actually we have the similar result for the derived category of coherent series and also the singularity category. Not only for the perfect derived category, we have the similar result to these two-landed categories. And the second statement is also actually more generous statement. Actually, the second statement is we can prove the second statement for general tensor triangulated category. If we consider the tensor triangulated category as the perfect derived category, we have this result. This is the main theorem. So since the second statement is a very general statement, so let me give an outline of the proof of the first statement. To this end, let me give two propositions. The first proposition is functoriality of triangular spectrum. Let T be a triangular category and U be its stick subcategory. And consider the quotient factor Q. Then this factor induces immersion of topological spaces from the triangular spectrum of T over Q, the quotient of T by U, to the triangular spectrum of T. We have this immersion of topological spaces, where this map is given by taking inverse image of X. So under the image of this map is this subspace, subspace of the triangular spectrum of T, consisting of parametric subcategories, parametric subcategories P, which contains U. So this map Q induces, so this map Q star induces a homeomorphism between this topological space and this topological space. And the next proposition, the second proposition is the following. Let X be an Italian scheme and X is a point. Then there exists an equivalence of triangular categories between this quotient, the quotient of the perfect derived category of X by S of X, which is equivalent to the perfect derived category of the local ring. Actually, we have this equivalence of triangular categories after taking idempotent completion. But taking idempotent completion does not affect to taking idempotent completion does not affect to the triangular spectrum. We can ignore idempotent completion. So using these two propositions, we can reduce the problem to local affine case. So using, let me give an outline of the proof of the first statement using the previous two propositions. By using the proposition, we have this homeomorphism and immersion. So, the first homeomorphism follows from the first proposition. second proposition. Indeed, this triangular category and this triangular categories are equivalent. So their triangular spectra are homeomorphic. And the immersion is, we obtain this immersion by using the first proposition. The triangular spectra of this quotient triangular category is embedded in this subspace. Sorry, this is a homeomorphic, and which is subspace of triangular spectrum of the perfect derived category. So we have these homeomorphisms. And under this homeomorphism, the prime-6 subcategory S of maximal ideal corresponds to S of X. Here, this six subcategory is prime by using the example I have explained before. Since this is a commutative ring, S of prime ideal is a prime-6 subcategory. So this 6 subcategory is a prime-6 subcategory of this perfect derived category. And we can easily check that this 6 subcategory sends to S of X. And since prime ideal sends to, prime-6 subcategories to prime-6 subcategories, the corresponding 6 subcategory S of X is a prime-6 subcategory. So this is the outline of the proof of the first statement. This is just a consequence of the previous two propositions. Okay, for the rest of this talk, I will give several applications of main theorems. The first two corollaries are a direct consequence of the main theorem. Let X be a Noetherian scheme. Then the first corollary is I have already mentioned before. This is a consequence of main theorem. For a Sikh ideal P, for a Sikh ideal P of the perfect derived category, P is a prime-6 ideal if and only if P is a prime-6 subcategory. Indeed, the implication from left to right is the first statement of the main theorem, and the converse is the second statement of the main theorem. So we have this equivalence. Also, we have the following corollary. Since S of X is a prime-6 subcategory, we have an injection from X to the triangular spectrum. The map is given in this way. X tends to S of X. And actually, this injection is an immersion of topological spaces. So topological space X is embedded into the triangular spectrum of the perfect derived category. And if we restrict the triangular spectrum to Sikh ideals, we have this homeomorphism. X is homeomorphic to the intersection of triangular spectrum and the set of 6 ideals of the perfectly derived category. We have this homeomorphism. And by this corollary, this intersection is equal to the TT spectrum, which is a set of prime 6 ideals. So in this sense, this immersion recovers Balmer's homeomorphism between X and the TT spectrum. These are direct consequence of main theorem. From the second corollary, in general, we have an immersion from X to the triangular spectrum. But in general, this immersion is far from homeomorphism. For example, let us consider the projective line over a field K. Then we have the following homeomorphism. The triangular spectrum of the perfectly derived categories of projective line is homeomorphic to the disjoint union of P1 and the discrete topological space G. And the composition of this natural inclusion and this homeomorphism is this immersion. So in this case, this immersion is not homeomorphism. And similarly, recently, Hirano and Ouchi proved the following theorem. Let E be an elliptic curve over a field algebraic, E be an elliptic curve over an algebraically closed field K. Then there exists the following homeomorphism. The triangular spectrum of the perfectly derived category of E is homeomorphic to this disjoint union. Disjoint union of E and ERD, where RD is an element of this set and ERD is a copy of E. So the triangular spectrum of this derived category is homeomorphic to the disjoint union of copies of E. And also the composition of natural inclusion from E to this disjoint union and this homeomorphism, the composition of these maps is equal to this homeomorphism, so this immersion. So in this case also, this is not a homeomorphism. So in general, the triangular spectrum is much larger than X. So next, let us consider some subspace of the triangular spectrum. Okay, now let us recall one notation. Let T be a triangular category. We say that a family of objects G lambda is a generating set if the smallest subcategory containing all of G lambda is equal to T. So if X is a 6 subcategory and contains X containing G lambda, then X must be equal to T. This is a definition of generating set. The following proposition is an easy observation about generating set under SIC ideas. Let T be a tensor triangle category, and let G lambda be a generating set. Then a given SIC subcategory X is a SIC ideal if it satisfies this condition. Tensor product of G lambda and an object of X belongs to X, or X is closed under taking tensor product with generating set. Indeed, if we consider this subcategory Y, which is a subcategory consisting of object M, such that the tensor product of M and X is contained in X, then we can easily check that this Y is a SIC subcategory, and by this assumption, this SIC subcategory contains all of G lambda. Therefore, since G lambda be a generating set, this SIC subcategory must be equal to T. Therefore, M tensor X is contained in X for all object M. So for our triangle category D path X, we use the following generating set. For example, this statement is given by Thomason. Let L be an ample line bundle on X. Then the set of tensor product of copies of L gives the generating set of the perfectly derived category. So if L is an ample line bundle on X, then for a prime SIC subcategory P, this condition is equivalent to say that P is a prime SIC ideal. Indeed, this implication is by definition of prime SIC ideal. And the converse implication uses the main theorem. Indeed, since this gives a generating set by using the previous proposition, just left-hand side implies P is a SIC ideal. And also, since P is a prime SIC subcategory, P is a SIC ideal and a prime SIC subcategory. So the main theorem shows this implication. SIC ideal and prime SIC subcategories implies prime SIC ideal. So we can check whether a given prime SIC subcategory to be prime SIC ideal or not by using ample line bundle. First, let us consider quasi-affine case. Recall that a scheme X is quasi-affine. This means open subscheme of an affine scheme. A scheme X is quasi-affine if and only if the structure C is an ample line bundle. And also we can, obviously, all SIC subcategory is closed under taking tensor product with the structure sheaf. Since the structure sheaf is a unit with respect to the tensor product. So applying the previous observation, we have the following corollary. Let X be a Noetherian quasi-affine scheme. Then X is homeomorphic to the triangular spectrum of dpfx. So in this case, we can reconstruct X from the triangular category dpfx. And also, if we consider the derived equivalence for Noetherian quasi-affine schemes X and Y, we have a homeomorphism F from X to Y, such that this homeomorphism induces an isomorphism of local rings. Local rings of X, local ring at X and local ring at F of X. So Stokes locally isomorphic. X and Y are Stokes locally isomorphic. Indeed, under this assumption, this homeomorphism F is given in this way. For a prime-6 subcategory S of X, this corresponds to a prime-6 subcategory. This corresponds to a prime-6 ideal of Y. And we define F by this formula. So we have an equivalence between the quotient of these two categories. And we have already mentioned before, this quotient is homeomorphic to the derived category of local ring. And here is also equivalent to this local ring. Since these are derived categories of commutative rings, the equivalence between these two derived categories implies these rings are isomorphic. So there exists an isomorphism between this local ring and this local ring. Next, we consider a projective goal line sign variety of dimension D. Then we consider this functor, taking a tensor product with this shift of canonical sheaf. Then it is known that this functor is the cell functor. Namely, this functor satisfies this functorial isomorphism. This is a derived version of cell duality. Using cell functor, recently Hirano and Ouch introduced the notion of cell invariant prime-6 subcategories. We say that a prime-6 subcategory P is cell invariant if it is stable under applying cell functor. And denote by spec triangle cell by the set of cell invariant prime-6 subcategories. Since the cell functor is given in this way, a prime-6 subcategory is cell invariant if and only if this condition holds. And if there exists a derived equivalence between the perfect derived category of X and the perfect derived category of Y, then since this is an equivalence of triangular category, this induces a homeomorphism between triangular spectra. So here is Y. And actually, this homeomorphism restricts to homeomorphism between cell invariant loci. Indeed, cell functors commute with derived equivalence. From this observation, Hirano and Ouch proved the following corollary. Let X be a projective Gorenstein variety with ample canonical or ample anti-canonical C. Then X is homeomorphic to the cell invariant locus. So as an application of this corollary, we have the following. Assume that there exists a derived equivalence between X and Y, where X and Y are, as in this corollary, X and Y are projective Gorenstein variety over K, satisfying this condition. Then, similarly as the quasi-affine case, there exists a homeomorphism F from X to Y, which induces an isomorphism of local rings. In particular, if X and Y are derived equivalent, then X and Y are birational. And Hirano and Ouchi also pointed out the following remark. If we further assume that X and Y are normal with dimension at least 2, and the base field K is uncountable algebraically closed field of characteristic 0, then by the result of Kohler, Lieblich, Olson, and Sabin, the topologies on X and Y determines their scheme structure. This topological space determines scheme structure. Therefore, this homeomorphism induces an isomorphism of schemes from schemes between X and Y. So together with this observation and their result, we can reconstruct a scheme structure on X from the derived category. And this gives an alternative proof of Bondar, Orloff, and Barat reconstruction theorem. The proof is completely different, but we have the same result by using their result. Okay, so I will finish this talk by introducing further problems about this topic. First problem is to define C-Hob rings on the triangular spectrum. I have explained in the introduction, TT spectrum have a ringed, locally ringed space structure. So it is natural to ask, whether we can define a C-Hob rings on this topological space such that this inclusion is a homeomorphism. This inclusion is a morphism of schemes. This is the first problem. And the other problem is the following. Let X be a smooth variety. Then for Fourier-Mukai partner, this means there exists an equivalence of derived categories. If there exists such an equivalence, we have the following immersion of topological spaces. Since these are equivalent of equivalence of triangular categories, these triangular spectra are homeomorphic. And by corollary of main theorem, Y is embedded into this topological space. So the Fourier part of Y is embedded into this topological space. If we denote this image by Y of phi, Y sub phi, then we have the following inclusion. The union of Y sub phi is embedded into the triangular spectrum of d bar X. So the question is, when does equality hold? This is the question. If the equality holds, this topological space parameterize Fourier partner. So this is, I think this is an interesting problem. Okay, now I will finish my talk. Thank you for your kind attention.
Oh, thank you very much. Okay, so are there any questions or comment to this talk?
So for two variety, we have a morphism between them. In general, could we construct the associative functor for the two construction you have?
So say again.
For morphism between two varieties, I'm asking, do we have a functor between your construction for X and Y?
I think the question is to ask whether the construction is functorial or not.
Actually, I don't have any answer. We only have this functoriality. We only have our functoriality with respect to the quotient functor. Other functors, I don't have any such a functoriality. Even if we consider the perfectly derived categories, I don't know. I don't have an answer.
Can I ask a question? So maybe you mentioned you have a similar result on singularity category, right?
Yes.
So what is the statement or?
The statement is we can define the similar 6 subcategory for the singularity category. This is the object of the singularity category whose stalk at X is isomorphic to 0 in the singularity category. Then the result is if the local ring is hypersurface, then this is a prime 6 subcategory. And the converse holds if structure C is as a local ring is complete intersection. So in this case, not all such a subcategory is such subcategory is prime, but we can characterize whether this subcategory is prime or not by using local ring at X.
Okay. Thank you. So, are there any question or comment? So if not, let's thank speaker again. So thank you very much.